Hello, welcome to today's presentation. In this presentation, I will talk about unsupervised generative adversarial attentional network with adaptive layer instant normalization for image-to-image translation, which is abbreviated as U-GAT-IT. This paper was written by these guys from Boeing Korean Engineering and Technology Center, and today the presenter is Isaac Thomas Nicholas from Dongseo University, Department of Computer Engineering, Lab of Machine Learning and Deep Learning. And the following is today's content, which we will go through by starting with definition of image-to-image translation. Image-to-image translation is a task of learning a function that maps image within the two domains. As we know that deep learning and neural network is a universal function approximator. So by learning some parameters, we will be able to find a function that can well map the input image to some kind of output. For example, in this case, we have a human face here. We want to map to an character. So we can do so by feeding in the human face to a neural network, and then by learn the parameter we can find these animation characters over here. And also we can take horse and generate zebra, or we can take cat and generate a dog. So this is generally called image-to-image translation task. This work was motivated by several things. One of them is attention mechanism. Attention mechanism is a mechanism used to focus in a specific features from an image. For example, here this image is being taken with a neural network, and we are trying to this neural try to give the caption to this image. So to do so, the neural network has to know where to focus and when to focus. So by picking different object from given image, it can generate some kind of useful text. For example, here we have human and boy, as well as a background which is garden or a park, and we see woman is throwing something to the air. Attention try to focus and try to find one object at a time and try to give a meaningful text. For example, here it finds a woman and it generates text. And the next one, it use is because it already try to concentrate on this single object. So this is a very powerful way to try to find the distinctive features from a certain domain by giving some kind of input. So this paper uses this idea to try to find the meaningful features from given input. Another motivation is geometric change between domains. Here we can see that there's some changes between two domains. First one is a human face. We need it to generate some kind of character anime, but you can see that there's some kind of some features from human have been changed. So for example, the size of ears, eyes are somehow different. The shape of the mouth as well as the size is also changed quite a lot. So this is one of the challenging problem in several grounds. And in this as a side, the case of Obama picture. So the model tried to generate another image which is resembles the reference image of Obama. As we can see here, reference as well and our and the output has no big difference between them. So most of the mod so as we can see between these two cases, the very challenging case is the second one, where the shape has to be changed a lot. So in this work they try to tackle this problem. There's two main contribution from this paper. The first one is try to use attention model, try to help the model to focus on a more important gradient which distinguish between the two domains. The one which we can say it's a source domain, and the other one is a target domain where we want to map the input to or the source to. And the second contribution is to use AdLIN. AdLIN is a combination of layer normalization as well as instant normalization. So by using learnable parameter, it can effectively work by changing or learning where it's instant normalization is really needed or important to be used, or where the instant normalization is better than the layer normalization. So in order to use this, then the model is trained in such a way that it can adaptively choose either to use layer normalization or instant normalization. So by combining these two features, the model can generally control the amount of changes to make in both shape and texture. Let's go to methodology of this paper by starting with model architecture. As we know that in this work they also use GAN approach, so we have two kind of network, which is generator and the second one is discriminator. So the generator will try to learn to generate a better output, and then the discriminator will try to challenging it by discriminate and tell the generator that your output is not good enough to be able to fool me. So the generator can use that feedback in order to train well. So let's start by generator. Generator composed of three main blocks. The first block is encoder, which will try to encode the input to some kind of feature map. Then we have auxiliary classifier, which will try to learn the imported weight using the encoded features. And we have a decoder, which is the most significant part of this network where the mapping takes place. So we will define and analyze the function or role played by each of these blocks. Let's get started. So we'll start with the downsampling. Downsampling is a process of mapping or reducing the dimensionality of a given input. So for example, here we have 8 by 8 input. Let's say it's an image. Then we downsample it to get a 2 by 2 image. We can get this result by using several techniques, but in this part I will show an example using max pool. Max pooling try to get the maximum pixel when we place a filter on top of some position on the image or given input. So for example, for the first time we'll try to put the filter on top of here. We'll get the maximum, which is 6, and then we'll will be like our first output. Then because we use thread of 2, so we will move 2 steps to the right and then try to find the maximum. In this portion here it's 8, so we'll take 8 as our output. Then we'll move 2 steps down because we reached at the end here, so we'll move 2 steps down and then find the maximum, goes to output, move 2 steps because right is 2, 2 steps to the right, find the maximum and put it as output. So we can see this represent these whole blocks by taking the maximum pixels for each part where we place our filter. So this is called downsampling because we reduce 8 by 8 image by half, by 1/4, which is 2 by 2 pixel. Then the output will be fed to residual block. But what is residual block and what are the roles of residual block? Let's see. So residual block is combination of several layers, and then we try to skip from by taking the output of one layer, skip several layers in the middle and then feed it to the deeper network. So for example here we skip several blocks and then we take the output of this activation function p_reru and then we feed it to the deeper layer, which is like embedding layer here. So by skipping this connection we form one block, one residual block. So we can put these several blocks in our network in order to create a very deeper network which can generalize presentation of a given input. But what is the function of residual block? It's believed that due to the rise of a problem called vanisher gradient during the learning process, this residual block tend to solve the problem of vanishing gradient. Vanisher gradient is whereby the gradient becomes 0, so this prevents the model from learning any longer. So by using residual network and take the output of certain layer and feed it to the other deeper layer, we will allow model to solve this vanish gradient problem, and allows model to create to have a very deeper network, which will which will lead to better representation and generalized representation of the different input. So the function of residual block is to solve the problem of vanishing gradient, as well as to help us to create a very deeper neural network. So after seeing the residual block, then this two downsampling as well as residual block forms what we call encoder in generator network, and the output of encoder, which in which each encoded map, feature map, represent the given input. We will feed them to auxiliary classifier. Then from auxiliary classifier we'll try to learn the important weight, and then after learning important weight it will combine the learned important weight with encoder to create what is called attention map. We will see in more detail in the next slide. So the function of auxiliary classifier is to learn the important weight of each feature map of given encoder value, given encoder map, and then pass it to some activation function, and then get the important weight, then use the important weight to generate attention map for each given encoder encoder feature map. Then after getting this set of domain specific attention feature map from auxiliary classifier by taking the important weight, then multiply by respective encoder feature map, then we will be able to get the attention map. Then this attention map will be fed to the next layer. We will see in the next slide. But the important thing to note here is attention map will generally capture distinctive features from each given input. So these distinctive features will be used by our network in order to get those features which are really important to generate useful and realistic images. So let's see what how this activator attention feature map are being used. So this attention feature map will be fed to full connected layer, and then will be used by full connected layer to learn these two parameters. So full connected layer will try to learn the gamma parameter as well as beta parameter. These two parameters will be fed to decoder and being used by adaptive residual network to do the actual mapping process. So our decoder here will become like this. So T means target, given the activation map of a certain input. X represents different input. At the meantime, for example, can be this human face being fed here. Then we get the attention feature map, then using attention feature map to generate some kind of output. So instead of giving the generator a plain input X, we are giving the generator attention feature map, which contain very distinctive features, and then very distinctive feature which can be used by our generator to generate a very nice output. So let's see how adaptive residual make use of learn the parameter gamma and beta, as well as attention feature map. So learnable parameters, which is our gamma and beta, which is being learned by a full connected layer, will be fed to a function AdLIN. Then AdLIN will decide whether how to generate this output. But how do we calculate these two? As we can see, this is an activation function with a bar at the top here, and also this is activation attention feature map, but with a bar at the top. So what does this to represent? Let's see in the next slide. So these two this is attention feature map for instant normalization, and this one with a subscript L with the bar, it represents a layer normalization attention feature map. So these two attention feature map normalize the form by using the mean, the two mean. These two means and these two standard deviation are channel wise and layer wise mean and the standard deviation respectively. So this will be utilized by using the given attention feature map, then subtract the mean and then divide normalize it with this, and then we will get a which is represent attention feature map came from instant normalization, and also we'll get the A with subscript L, which represent attention feature map after performing layer normalization. So the AdLIN function will use given attention feature map, then the learnable parameter gamma and theta in order to control or to adjust, and then to decide whether to perform the instant normalization or layer normalization. But how does a model decide whether to perform instant normalization or layer normalization? Let's see. So in order for model to be able to decide which one to perform, it tends to learn this function over here. So by learning this value over here, when this value is close to 1, then the model will perform instant normalization, and when this value is equal to 0, then the model will perform layer normalization. So when this value is equal to 1 means instant normalization is more important to be performed, and when it's equal to 0, then layer normalization is more important. And normally this value are being initialized. For example, this value will be initialized to 1 at the residual block in the decoder, and this value will be initialized to 0 at upsampling block of our decoder. So these two will control how much the amount to apply to change the amount of texture or the shape of a given input in order to generate some kind of output. So this will play a greater role in this to making decision to perform instant normalization or layer normalization. By doing so, we can control the amount of shape and texture that we want to apply on a given attention feature map. Then what happened to the upsampling? During the upsampling, the given input will be the model will try to generate some kind of output which will match the size or dimensionality of the given input. So we can do so by several techniques, but one example of upsampling is nearest neighbor. Nearest neighbor will try to place around the given pixels. For example, here is 2 by 2. We'll try to duplicate this value, for example 1 at the top and at the left, and then diagonally. We'll try to surround it with the same pixel, believing that these neighbors will try to follow this pixel, as well as 2 will try to at the top, right, and diagonal will put the same. 4 and 6. By doing this, we will move from 2 by 2 to 4 by 4. So here we increase the dimensionality of our output. So this is about generator. So let's move to the second part of our network, which is discriminator. So discriminator follow almost the same structure. So we have downsampling encoder here, we have auxiliary classifier, and also we have a discriminator or classifier. And during the downsampling, it will perform the same thing, which is dimensionality reduction. So for example, given 8 by 8 to map it to 2 by 2, and then the encoded value will be given to full connected layer in auxiliary classifier. Then auxiliary classifier, in this case, it will act as a discriminator, so it will try to discriminate the given input, whether it comes from the target or it comes from the generator. By make use of encoder feature map, as well as lengthy important ways to generate activation feature map. So this activation feature map length will be a greater help to our discriminator or classifier here to importantly find these features which try to fool our discriminator. So if the sample came from generator, this auxiliary classifier will try to find exactly this attention feature map which differentiate the given input if it came from target or from source. And then by doing that, it will be much greater help to our classifier here, because now the classifier will have to wait just a little bit, add more little bit effort in order to decide whether this come from the target or from the generator. By using sigmoid convolution layer, it will output 0 or 1. 1, for example, can be that the image come from the target, 0 for image that come from the generator. So this is a complete network, which is a generator as well as discriminator to form to accomplish this web. So as we know that now the classifier will not be fed with X direct, but instead we'll use the attention feature map which land from auxiliary classifier, in which this attention feature map are very distinctive features land from the given input. So our classifier or discriminator will make use of attention feature map of a given input X to make a prediction whether this given input come from target or come from generator. So this is how uh, the whole process taking place, and all the calculation as I have shown and explained on previous. Okay, let's move on in the loss functions. So generally in this paper they discuss four functions to make an objective function. So the first loss function is adversarial loss. Adversarial loss try to find if the generated or mapped image follows well the target image. By using the least square GAN function instead of using vanilla GAN. In this paper they use least square GAN function, in this in which this function tend to smoothly learn and try to use the function that provide the smoothly and non-saturating gradient in this denominator D, where we want to pull the data generated by the generator. This one we want to pull it toward the real data, so toward this real data or real distribution. In this case we can say X target, so that the G generator data that are similar to the target. So by doing this we guarantee that it will be stable during the training process. So our discriminator will try to minimize this function by making this even lower. So by doing that we can guarantee that our discriminator do the better job. In generator side, generator will also try to fight back by trying to minimize this part of the loss function, whereby giving its output, it will try to fool the discriminator to output to give the high score on this given input. That discriminator to classify this as a real, so that if it gives a high score here, it means that the difference will be minimum. By doing so, it will guarantee its succession. So this is adversarial loss. So by trying to minimize respectively according to which side it will favor in. So for discriminator, to try to minimize the general function, and this generator will try to minimize the confidence of discriminator. Next we see we have a cycle loss. Cycle loss is trying to solve the model collapse problem. In this case we will give the input as well as the generated or translated input, which in this case we have X here, which can be like this human face. We fed it here, then we translate it from this source domain to this target domain, and then after getting this we'll check this again and feed it to this generator again and try to recreate or reconstruct this human face over here. Then we try to find the difference between the given image and the output of the generator after feed this anim character over here, and then try to reconstruct it. So this represents a real image and this represents a reconstructed image. So the difference, as the difference goes low, we try to find the constraints which will be consistent, and the model will not face a model collapse problem, in which the model collapse refers to a situation in which the generator part of the network generates only a limited amount of varieties of samples regardless of the input. This means that when the network is trained upon a multimodal data directly, the generator learns to fold the discriminator by generating only a limited varieties of data. So this will help our network to alleviate the model collapse problem. Another loss function is identical loss. Identical loss will try to find if the generated image color follow the input or source domain. So by finding the difference between each pixels will give us the difference how far the given input like human face color differs from this generated or anime character over here. So the lower the better. So by lowering this difference, it means that it guarantees the similarities between the two images. So the given input and the generated image after feeding in this given input. So this will guarantee us to get the similar colors as a given input. The other loss function and the last loss function is a very important loss function because this one try to teach the model about which features at that state are very crucial and very important to distinguish between the these two domains, which is source domain as well as target domain. So by using this function, we will guarantee that the model can learn very distinctive features, and then if it learns well, then the loss will be lower and lower. And we see this being used auxiliary classifier. Auxiliary classifier will be feeding with the generated image from our generator. Then we try to find the square of the difference between of this one and the probability generated by auxiliary classifier. So this generated probability represent how confident that the auxiliary classifier is at classifying this given input. So it can be the real input or it can be the generated input. So this will guide the model to find the very distinctive feature between the two domains. And at last we have a full objective function. Full objective function is a combination of all the loss functions that we have been discussed. So we have four loss functions. We have gun gun loss, we have cycle loss, and we have identity loss as well as cam loss. So also we have penalt constant variable here, hyperparameter. So we have 1 up to 4 with different values. This is to symbolize how important the function is to contribute to this learning process. So by giving these different values, it tend to increase or to decrease the confidence of the model by helping it to guide it into a right direction by penalize it with huge penalty if it's do bad, but reward it more if it do well. So this finalize learning process and the model architecture as well as loss function of this paper. So moving to the experiment part, this is some of the outputs that I was trying to do the implementation by myself, try to see how does instant normalization work. So as we can see, this I feed in this image and then I got this output. So this is to show how instant normalization affect given input. So this is the effect. It shows the instant normalization, uh, how it affect the given input. Here we see different output. We visualize of the attention feature map for various data sets, and then the first was as a source image. So this is the source image, and the second one we are given attention map of the generator, and the third one to the two more features which I didn't really include here. So these are the output of our generator. So as we can see here, it has done a really great job by learning this. So here we can see how important attention feature map are in finding the very important features and try to know the rest. So for example here, yeah, we can see the color and texture and everything that makes up the like animal, which make which represent the animal, or which represent the face of human, or which represents the landscape, and so on. So this is how well the attention works. And this other output by comparing different kind of gun. So here we have several gun and several output, including this paper's output. So in A column we have source image, and then in B column we have output of this paper. In C we have this output of this paper, but they try to remove instant normalization at decoder by using only instant normalization in encoder with CAM. And then D try to use layer normalization only with CAM. So we can see how important maybe like layer normalization is in this part, whereby we try to in this part they try only to use instant normalization. So instant normalization tend to lose some features. But also if we remove instant normalization and use layer normalization only, we try to we can also lose some important features. For example, in this part we lose like color of the eyes, the shape of the mouth, and this general structure, the shape of the output. So this is the difference between the importance, to show the importance of each pair component of the model. At E here, it's a result of using adaptive instant normalization with CAM. So by using adaptive, it somehow follows and even far better compared to only instant normalization. But using adaptive normalization, we see the output is quite great. And also here they tried only to use and with the CAM, to see how it really gives the effect. So these are different output by removing one of the component. And this is a table which represents the scores, different score, by removing or adding something. So here, for example, without instant normalization, this is a score. By using all the components, we can get this score. By using layer normalization only, we can get this score, and so on. So this table represents and shows the importance of each component also. Here it's a general model comparing with other approach. For example, U-GAT-IT and Psychogan unit and other function. We see that like it outperform almost all in all data set except the last one, which is little just a minor difference between the two, as we can see. So only few points away from the state of the some of the state of the technique. Conclusion. So detailed analysis of various experimental results supports the assumption of the authors that attention map obtained by auxiliary classifier can guide generator to focus more on distinctive regions between source and target domain and help the model to generate better and realistic images. And another one is about AdLIN. So they found out that AdLIN is essential for translating various datasets that contain different amount of geometric and style changes. So it performs well by keeping and reserving and as well as generalize well on generation of texture as well as the structure of the output. So by doing so, they using these two approach, they show that how much each of these guarantees the output. In discussion part of for improvement, I suggest that you're using capsule network. Capsule network is a kind of network which not only try to find part of sub parts of the image and try to abstractly classifies it as a certain image. For example, here we have the face, eye combined with eye, mouth, and then nose to make a face. But this is not like arranged a human face. But this is output of CNN. CNN can just predict and say this with confidence of 95% that this is a face. But capsule network will have to find exactly match human and the position of each component so that to classify it as a human face or else. Also, capsule network is good to work with any pose or any angle. So by using capsule network, we can guarantee that the model, because this is tend to this focus on the selfie, so that we know that human can take selfie at different angles. So by using capsule network, we can guarantee that the model can learn well. So this, as we can see here, this is one of the output when I was running some experiment, and this is a CNN model. This, as we can see here, the eyes and the eyes, they try like they fail to align well and try to follow the given input, and somehow getting it is really difficult because this is after more than 8,800 iteration, but still the model couldn't really learn so well to even align these two images. So I suggest capsule network because of the following reasons. So the capsule network lends a more robust representation for each class that a traditional convolution couldn't, and because there is a natural variation in skew, rotation, style, angles, and so on, which a capsule network can solve this kind of problem. Dynamic routing, which is a feature in capsule network, it can be viewed as a parallel attention mechanism. So we have several attention mechanisms inside this capsule network, which can guarantee that the model can focus on a very important features and ignore the rest which are not really important to differentiate between the domain. So these are my suggestions. These are some of the reference, and thank you for listening.